Hello, let's continue our discussion of diffraction phenomena. So just as a recap, last time we looked at diffraction gratings, which are basically the combination of many slits. And we found that the condition for maxima is that the slit distance d, the distance between neighboring slits, times the sine of the angle under which we look at it, must be equal to an integral number of wavelengths. And we can turn this around in a spectroscope or a spectrometer where we measure the angle and then thereby determine the wavelengths. What I would like to start with is I would like to demonstrate how you get from a single slit to double slit to multiple slits, finally to the diffraction grating, how the interference pattern changes. We start with a double slit. We can see both the maximum and the minima of the diffraction on the slit itself, as well as the multiple maxima coming from the interference between the two slits. So let's now go to, I think the next one you have is 3 slits. Oh, this is 3 slits already, okay. So now let's go to 6 slits. And what you can see is that the maxima are getting brighter and brighter compared to the minima. So now let's go to a real diffraction grating with thousands of slits. And you see one maximum here, and the next maximum here, and the next maximum here, and there's also one over there. And there's basically no light intensity in between. We can also see how that changes when we change the wavelengths. So let's try the red laser with this. So this is now 650 nanometers. And if we sort of remember, we have a maximum here in the middle of the screen, and we have the next maximum sitting over there, roughly at that point. With these tools at hand, the diffraction grating, we can enter the science of spectroscopy. So if we have a heated gas or solid, for example, the sun or a light bulb, then a continuous spectrum is emitted. And we can image this continuous spectrum using a grating. Other light sources, they can have just various spectral lines, like, for example, this is hydrogen gas, this is mercury, this is sodium. And if we look at the sun, the continuous spectrum of the sun, we actually find that some of those lines are reproduced, but as shadows. And what that means is that we have light getting absorbed by those gases present in the upper reaches of the sun. So that's considered an absorption spectrum, because you see those as dark lines rather than as bright lines. But the principle is the same, that the grating turns wavelength into angle, basically. So let's calculate another example. So let's assume we have hot hydrogen gas, and that is observed with a spectroscope using a diffraction grating that has 10,000 lines per centimeter. And the spectral lines that are nearest to the center, where center means 0 degrees, is a violet line at 24.2 degrees, a blue line at 25.7 degrees, a bluish-greenish line at 29.1 degrees, and a red line at 41.0 degrees. And the problem is to determine the corresponding wavelengths. And so we start solving this problem first by considering the lines nearest to the center. That means that the order of the diffraction pattern is 1, as it is usually the case when one uses a spectroscope. We calculate the spacing between neighboring lines, that is 1 over the 10,000 lines per centimeter, which means this is 10 to the minus 4 centimeters or 10 to the minus 6 meters, or 1,000 nanometers, which is a convenient unit to use. And we can now use the formula for the maxima. So first for the 24.2 degrees, we multiply the 1000 nanometers with the sine of 24.2 degrees, and that gives us 410 nanometers, which is indeed in the violet. Very close to the one that we actually saw on the screen. That was 405 nanometers. Then for 25.7 degrees, we find 434 nanometers. Then 29.1 degrees gives us 486 nanometers. And finally, 41 degrees gives us 656 nanometers. Also very close to the red maxima that we just saw, which was 650 nanometers. So let's look at a different example. There's actually one problem with using gratings, and that is that the different orders of the spectra can overlap. So let's assume we have white light in the wavelength region between 400 nanometers and 750 nanometers, striking a grating that contains 4,000 lines per centimeters. The problem is to show that the blue of the third order overlaps the red of the second order. And to do that, we proceed in the same way as before. We find the spacing between lines, 1 over 4,000 per centimeter, which gives us 2,500 nanometers of spacing between neighboring lines. And now we can calculate the third order for 450 nanometers. This is 3 times 450 nanometers divided by 2,500 nanometers. And that gives us a sine of the angle of 0.54 if we divide those two numbers and multiply by 3. And for the 700 nanometers, it's the second order, so we just multiply by 2, and we get 0.56 for the sine of the angle. And we observe that this sine is bigger than that sine, and that means that the corresponding angle is bigger than that angle. And that means that the spectra actually overlap. And so one has to be careful when looking at the spectrum that you're not fooled by the higher order maximum.
Where do you get the 2.5? I'm not
The
sure.
2,500 nanometers?
Yeah.
That's 1 over 4,000 per centimeter. So we have 4,000 lines per centimeter. If you want to know how close together our neighboring lines, then we need to take the reciprocal value of that. So 1 over 4,000 is 2.5 times 10 to the minus 4. And if I then calculate from centimeters to nanometers, I get 2,500 nanometers. Just like in the previous problem, we had 10,000 lines and we got 1,000 nanometers. Let us now look at a different wavelength region. The very first Nobel laureate after the Nobel Prize was established was Wilhelm Röntgen. And he found out that if you smash electrons that were accelerated by a high voltage, typically 30 or 150 kilovolts, if you smash them into a glass or metal surface, then X-rays are emitted. These X-rays, or sometimes also referred to as Röntgen rays, are electromagnetic waves with rather short wavelengths, something like 0.01 nanometers to 10 nanometers. And those X-rays penetrate different materials to different degrees. And so soon after the discovery of X-rays, Röntgen took the first X-ray from his wife's hand, and you actually see they were married because she's wearing her wedding band. And probably getting bone cancer as a consequence. So be careful when agreeing to marry a physicist. We are not really concerned with medical X-rays, but rather with X-ray diffraction, because even though the wavelength is short, X-rays can still diffract. We cannot use a usual grating because the line spacing would have to be very, very close, and you cannot actually manufacture such gratings. However, this fellow had an idea of using crystals instead. And crystals are regular arrangements of atoms or molecules. And those have the right kind of spacing on the order of 1/10 of a nanometer or so. If, for example, we have sodium chloride, which is a regular cubic lattice, then we have all those atoms sitting at regular places. And if we assume that each one of them emits a Huygens wave, then we can calculate the path difference that is observed under a certain angle phi. And be careful, this angle phi is now not the angle with respect to the normal, but with respect to the surface. So before the angle theta was always with respect to the normal. Now we are looking at the crystal surface. So if we have this angle phi between the surface of the crystal and the reflected X-ray, then this angle repeats here because this line is perpendicular to that, and that line is perpendicular to the crystal surface. And therefore the path difference between the Huygens waves is d times the sine of that angle. And we get a similar condition for maxima, that this path length has to be an integral of the wavelength. And this is now called the Bragg equation with two g's. And again, phi is not the angle with respect to the normal. Also, the X-ray reflections on crystals is more complicated than a simple grading, because you can consider different planes in a crystal. For example, instead of just looking at that plane, I can look at planes like these, and they have different spacings. Not all spacings are allowed, but more than one spacing is allowed, and therefore you get something like this, many dots in a picture, in an X-ray picture. And this is kind of like a fingerprint, a diffraction fingerprint of a particular crystal, and you can identify crystals or their crystal structure by looking at those diffraction patterns. And a very famous example was basically exactly 60 years ago, the structure of the DNA, the double helix structure, was unraveled using X-ray diffraction. And so this woman actually took the conclusive X-rays. Here's her picture that showed the helical structure of the molecules. And the characteristic pattern is this sort of X shape that you can see in the maxima. And unfortunately for her, she died too soon to receive the Nobel Prize herself, so only her co-workers received the Nobel Prize for this groundbreaking work in biology. I want to conclude our discussion of diffraction with the observation that you get diffraction even when you don't have apertures. For example, the closest real-life representation we have of our light rays that we considered in geometric optics are laser beams, like my laser pointer here. And those can be represented as Gaussian beams. And with Gaussian beams, we mean that the intensity as a function of distance away from the beam, the radial distance, looks like a Gaussian function. So I've plotted one here. And so we can define some effective beam radius or diameter, which we call W. And as it turns out that if you have a sharply defined beam like that of a flashlight or so, then it will diffract as if it went through a circular aperture, and therefore it will eventually produce something that looks like an airy disk radial profile of it. So it will have maxima and minima. Gaussian beams are different because they diffract as Gaussian functions again. So in other words, they keep their shape even after propagating. However, they still widen due to the diffraction. And so we define the smallest beam profile as the waist of the laser beam. So every laser beam has one point in space along its propagation direction where it has the smallest beam diameter. And here's a calculation of the intensity pattern at one instant in time of such a Gaussian beam, and it looks like this. So we have the waist here placed at 0. And then you can see that the wave fronts are getting curved as you move away from the waist. And the beam is slowly getting wider. To make this visible, here the wavelength is rather long, 30 millimeters, and the waist is very closely matched to the wavelength. So for a laser beam, the waist is much, much bigger than a wavelength, and therefore the widening of the beam is not as apparent. One can derive a formula for the beam divergence, meaning how fast the diameter of the beam grows with propagation distance, which is sort of similar to the Rayleigh criterion that you learned. The Rayleigh criterion was that it's 1.22 times the wavelength over the beam diameter. And here it is simply the wavelength divided by pi times the minimum diameter, which we call W0. So that means that if we propagate a distance L from the waist, then we get a waist at that distance, which is approximately L times the wavelength divided by pi over this minimum distance. Such formulas don't just apply for the simple Gaussian beam like this, but you can actually superimpose transverse modes, which are kind of like the vibration modes we found on a string, for example, only in 2 dimensions. And so the Gaussian beam spot looks roughly like this, but depending on how you tune your laser cavity, you can also get more complex patterns like those. In general, the more complicated such a pattern is, the bigger this emittance angle will be. So you get the smallest growth of the beam for a Gaussian beam. So that is what you usually are trying to achieve. So let's look at an example for such Gaussian beams. A somewhat famous example. The Apollo 14 mission left an optical reflector on the lunar surface. And that reflector can be used to measure the distance to the moon, between moon and Earth, very, very precisely. And what one does is one shoots a laser beam up to the moon, then it bounces off that reflector and then is observed back on Earth. And from the time delay of that laser pulse, you infer the distance. If we assume that the laser has a wavelength of 500 nanometers and a waist of 1 meter radius at the surface of the Earth, the question is how big from diffraction alone would be the spot size of that laser on the lunar surface? And how big would it be for one of my laser pointers, which has a waist of perhaps roughly 0.5 millimeters? And to do that, we use this formula which tells us how the divergence angle is related to wavelength and waist. So for 550 nanometers, we get 1.75 times 10 to the minus 7 radians. And plugging in the distance to the moon, we get a beam spot of 67.3 meters, which is much larger than this reflector here. For the pointer, actually, because the waist is so much smaller for the pointer, it would be a spot size of 130 kilometers. And that means that almost nothing from the intensity would get reflected back, because, of course, only the part of the beam spot that hits the reflector is reflected back. This diffraction has other consequences also. Let's consider that the Death Star from the Star Wars movies is orbiting around Mars and is threatening Earth. Let's assume that Mars at that point is in opposition, meaning the closest distance to Earth, which is about 78 million kilometers away. And let's assume that it fires a single shot that lasts about a second, and it hits the ocean, which is very likely since 2/3 of the Earth are covered by oceans, and evaporating a column of water 4 kilometers deep all the way to the ocean floor. The question is, how much energy is needed for such a shot? We assume 2.26 megajoule per kilogram of vaporization heat that is required for water. So we don't even consider heating it up to 100 degrees Celsius just for evaporating it. So we first calculate the impact radius of that shot. So we get our 78 times 10 to the 9 meters of distance times, everybody knows this is a green laser, so 500 nanometers. and divide by, let's assume that we have a 10-meter thick super laser from the Death Star. So if you plug in those numbers, we get an impact radius of 2.5 kilometers on Earth, and that corresponds to an impact area of 19.4 kilometers square. And if we calculate the water volume, that gives us about 80 kilometer cubed. So that has a mass of about 80 times 10 to the 12 kilograms, and we can now calculate the energy required to vaporize that much water. And it's about 1.8 times 10 to the 20 joule. Just for comparison, one of the world's most powerful lasers, the NIF laser at the Lawrence Livermore National Laboratory near San Francisco, can fire 2 times 10 to the 6 joules in one single shot. So my recommendation would be, when this shot is threatened, to not reveal the location of the secret rebel base, but rather wait it out, because most likely Earth will survive. It actually would survive a shot like this because it doesn't drill into the core. However, I would also advise to move as far away as possible from the location of the laser, because I don't want to be near a device that is trying to handle 10 to the 20 joule. Any small inefficiency and it will, the laser itself will be completely destroyed. Let's now switch gears a little bit and talk about a different effect that we can observe for light, and that is because light consists out of transverse waves. To introduce the subject, let me do a little experiment here. Very old-fashioned technology. I don't know whether you've ever seen that. So we have here a so-called Polaroid, which absorbs a certain fraction of the light. And if we place another Polaroid, then more light is absorbed. But if we actually rotate it, then all of the light is absorbed. A Polaroid is an example of a polarizer. So we can think of a polarizer as a kind of like if we had a rope, then polarization would correspond to the two different types of motion that are perpendicular to the propagation direction. The rope can move vertically, or it can move horizontally like this. And those would be the two different polarizations of a transverse wave on a rope. So we could then imagine a polarizer, which would be a slit that's oriented either vertically or horizontally. And if we have a vertical slit, then the wave can actually pass through unhindered. However, the opposite polarization would actually bounce off against the slit. So for electromagnetic waves, the analogy is that we consider the electric field vector, and that is the polarization direction. So if you have a light beam going like this and the electric field vector swings like this, then you would have a vertically linearly polarized electromagnetic wave. And if the electric field vector is in the horizontal plane, then it would be horizontally polarized. And these polarizing filters or Polaroids that I showed you, they actually consist of long molecules that are arranged parallel to each other. So if we have such long molecules indicated by those double arrows like this, if you now have an electric field vector that is horizontal, then the electric field will perform work on the charges in the molecule. And it's very easy to do that because charges can move along the molecule direction. However, if you have a vertically polarized electromagnetic wave, then the charges can't move, and therefore the wave performs no work. If the wave performs work, it loses energy, and that means it gets absorbed. So in other words, this acts like a vertical polarizer, meaning that only waves that are vertically polarized pass through unhindered, and the horizontally polarized ones are absorbed. And therefore, if we now cross two such filters at 90 degrees, we absorb both polarizations, and that means that we absorb all the light. If we put them at any other angle, then we observe that the intensity as a function of that angle is the total intensity times the cosine square of that angle. If we have now a setup with unpolarized light and two of those Polaroids, then we use the first one as a polarizer and the second one as an analyzer. And what that means is that the polarizer converts the unpolarized light, which we consider to consist out of an equal admixture of horizontal and vertical polarization. And it passes through the polarizer, and then it's completely vertically polarized. And then we place an analyzer at some angle, for example at right angles, to find out what is the polarization direction. Again, then the intensity that is observed is the intensity after the polarizer times the cosine square of the tilt angle. And of course, the first polarizer cuts the intensity by a factor of 2 because we just cut one of the two components. And since we assume they are equally mixed between horizontal and vertical, we just lose the horizontal component. So let's consider an example. Let's assume that we have unpolarized light passing through two Polaroids, just like in the picture that I just showed. And the axis of one is vertical and the other one is at 60 degrees. And the problem is, what is the orientation and intensity of the transmitted light? And so, as a first step, the intensity after the first Polaroid is simply 1/2 the total intensity. And after that, it's vertically polarized. Then, once it goes through the second Polaroid, the intensity is this intensity, 1/2 the original one, times the cosine square of 60 degrees. Cosine of 60 degrees is 1/2, and therefore cosine square of 60 degrees is 1/4. And therefore, the intensity after the second Polaroid is 1/4 of the intensity before the second Polaroid, or it is 1/8 of the original intensity, since that is 1/2, since the intensity after the first Polaroid is 1/2 of the original one. And the final polarization, of course, is linear and at 60 degrees with respect to the vertical. After a Polaroid, the polarization is always in the direction of that last Polaroid. So let's consider another example, but let's first do that in experiment rather than in reality. Let's now look at 3 Polaroids. So here I have my 2 Polaroids, and let's cover it with a third one that we tilt at 45 degrees. And nothing particularly spectacular happens because where they overlap, it's still dark. You can't have. However, if we take this out and place it in the middle between the two, then it's no longer dark. Actually, you can't. I can see it when I look down here. But yeah, it's a little bit tough to see on the screen because we don't have enough intensity. Turn the lights off, then it'll be clearer. Yeah, you can see that this is the area where just the 2 Polaroids are crossed. And that's completely dark, but there's actually some gray area here, which means that some light is going through. So we can now look at this mathematically using the equation for the intensities. And we trace it just like in the previous problem. So after the first Polaroid, we get polarized light, so we lose 1/2 of the intensity. So that was, say, the vertical polarizer. Now we hit the one that is at 45-degree angle. So that gives us an intensity that is the intensity after the first polarizer times the cosine square of 45 degrees. And the cosine of 45 degrees is 1 over square root 2. So the cosine square of 45 degrees is 1 over 2. So we lose half the intensity that we had before that second Polaroid. And now the big difference to not having this Polaroid in the middle is that now not only the intensity is reduced by a factor of 2, but also the polarization is changed from the vertical to 45 degrees. So if we now trace it through the third Polaroid, it is also 45 degree angle, because those two are 90 degrees with respect to each other. And that means we lose another factor of 2. And so our total intensity loss is a factor of 8 compared to the original intensity. But we don't lose everything, like we did with just 2 polarizers crossed at 90 degrees. So there are other ways you can polarize light than using Polaroids. When we looked at reflection and refraction, we actually did not consider polarization, we just used geometric optics. What's really happening at a reflection and refraction, let's say from air into water, is a little bit more complicated than just Snell's law and the law of reflection. One actually has to consider 2 polarizations. One first defines the plane of incidence. That's the plane that contains the incident ray, the reflected ray, and the refracted ray. So in this case, this is simply the plane of the screen. So that's one polarization. That's the one that I consider to be parallel to the plane of incidence. And then the opposite one is going in and out of the screen. That is the perpendicular polarization. And one can derive from Maxwell's equation formulas for the amplitude of the reflected wave compared to the incident wave, as well as for the refracted wave. Let's just now look at the reflected ones. So if the indices of refractions are n1 up here and n2 down here, then for the perpendicular case, we get this ratio of amplitudes. And for the parallel case, we get a very similar ratio of amplitudes, but n1 and n2 are switched. And that has a very interesting consequence. If we assume that there is a 90-degree angle between, as drawn in this picture, between the reflected and the refracted ray, then we know that the sine of the incident angle is the cosine of the refracted ray, or of course the sine of the reflected one. And the sine of the refracted ray is the cosine of the incident angle, or the cosine of the reflected angle. And that's simply because they are at 90 degrees with respect to each other. And if we now look at this formula, we can use Snell's law as well as those two relations. So n1 times cosine theta refracted is n1 times sine theta incident. So that's this equation here. Now we use Snell's law, which tells us that n1 times sine theta incident equals n2 times sine theta refracted. And then we use this equation, which gives us that this is n2 times cosine theta incidence. If we now look at this being equal to that, that means that the numerator here vanishes completely. And what that means is that in this particular case, there is, for the parallel polarization, there's no reflection happening at all. The entire beam is refracted. This particular angle is called the Brewster angle. And under the Brewster angle, we observe 100% polarization, even if the incident light has been unpolarized, because one of the two polarizations is completely refracted. And so in the reflected wave, only the perpendicular case survives, indicated by those dots here. So one can make use of this Brewster or polarizing angle by taking, in photography, for example, if you take an image of a picture of a pond, and you use a polarizer oriented in the right way, then you can all but eliminate the reflection, because we know that the reflection at the right angle is 100% polarized. And what you reveal is then the light coming from the ground of the pond. So this is the picture with a polarizer, this is the picture without a polarizer. The question is, what is this angle, this polarization angle? So we know that refracted ray needs to be perpendicular to incident ray for this to work. We can now look at the tangent of the incident angle, and that is the sine of the incident angle divided by the cosine of the incident angle. And that is the sine of the incident angle divided by the sine of the refracted angle, simply because of this relation. And from Snell's law, we know this must be n2 over n1. So in other words, the relation for the polarizing or Brewster angle is that the tangent of this angle theta p must be the ratio of n2 over n1. So let's finish with one example about that. So the question is, what is that incident angle where sunlight reflected from a lake is plane polarized? And what is the refraction angle? So if we just plug in this newly derived formula for the tangent of the polarizing angle, then we know that n2 over n1 in the case of air and water is 1.33. And we can simply apply the inverse tangent function and get that the Brewster or polarizing angle is 53.1 degrees. And we can now use Snell's law to find the refracted angle. So the refracted angle is the sine of this Brewster angle divided by 1.33, and that gives us 0.601. And if we solve with the inverse sine function for theta refracted, we get 36.9 degrees. And indeed, as it should be, the polarizing angle plus the refracted angle add up to 90 degrees. So, thank you very much. Oh, you have a question?
Is there any interaction with the magnetic field, or is that just no interaction?
There's of course interaction with the magnetic field also. It's just you can pick one of the two, and usually you pick the electric field because it's easier to see how it acts on charges. Most of the interactions are stronger electrically than they are magnetically, but in principle both give you equivalent viewpoints.